When a volcano erupts, the lava eventually cools into stone, leaving behind an environment wiped clean. There are no trees, there are no insects, there is absolute silence. To the human eye, this landscape appears locked in a state of permanent death. Without soil to anchor roots or retain moisture, rain simply evaporates or runs off the impermeable rock. The surface is hostile to life. Yet, in biology, empty space rarely remains empty. This desolate expanse of rock is a blank canvas, waiting for a specific sequence of colonization to begin. The process that follows is called ecological succession. It is a structured, directional sequence of events where organisms arrive, alter their environment, and slowly transform bare rock into a complex, living ecosystem over hundreds or thousands of years. Every forest and grassland on Earth was built this way. Terrestrial life relies on this invisible architectural process to construct habitable worlds out of absolute nothingness. To see how this construction begins, we have to look close to the ground. When ecosystem building starts from absolute zero on solid rock, it is known as primary succession. The first colonizers to arrive are pioneer species. These are usually lichens and mosses, organisms with unique biological adaptations that allow them to survive intense ultraviolet radiation and an environment lacking even a trace of soil. This diagram shows the mechanism of their survival. A lichen is a symbiotic partnership between a fungus and an algae. The algae produces food through photosynthesis, while the fungal threads penetrate microfissures in the rock. The fungus secretes weak acids that chemically dissolve the stone, extracting vital minerals and creating a fine mineral dust. As generations of these pioneer species live, die, and decompose, their organic residue mixes with the mineral dust they've created. Very slowly, they build up a dark, nutrient-rich layer of primitive soil. That first millimeter of manufactured soil is the crucial threshold. Once it exists, the bare rock is gone, and the environment is capable of supporting more demanding forms of life. Wind and passing birds drop seeds into this new soil layer, triggering the intermediate stage. Grasses, herbs, and ferns take root, rapidly expanding their coverage across the landscape. These intermediate plants act as biological engineers. Their root systems break up the ground further, altering the soil chemistry and increasing its ability to hold water. This moisture and plant matter invite the first waves of insects, worms, and soil microbes. The ecological complexity continues to escalate. The improved soil conditions allow larger shrubs and fast-growing trees to move in. Because these taller plants block the sun, they outcompete the pioneer species, reshaping the local microclimate by lowering ground temperatures and reducing wind speeds. Eventually, shade-tolerant hardwood trees establish themselves beneath the canopy, growing tall enough to dominate the landscape. The environment finally reaches its climax community, a mature, stable state where a high diversity of species coexist. In this climax community, energy flows efficiently through complex food webs, and the recycling of nutrients is balanced. Over thousands of years, succession has engineered a functioning ecological order. But a climax community is not permanent. Ecosystems face constant external pressures, and they remain vulnerable to sudden environmental shifts. A lightning strike sparks a wildfire. In hours, flames sweep through the canopy, decimate the forest structure, and kill centuries of growth. In the immediate aftermath, the smoke clears to reveal a charred, blackened landscape. Visually, this burned terrain mimics the absolute zero of the volcanic rock we started with. It appears lifeless. Yet there is a critical, hidden difference. Beneath the thick layers of ash and charred wood, the environment's most valuable manufactured asset, the nutrient-rich soil, has survived the heat. Because the soil infrastructure remains, the forest has been strategically reset rather than destroyed. The foundation for the next stage is already in place. When nature repopulates previously inhabited land, it deploys an accelerated recovery protocol known as secondary succession. This timeline compares the two processes. On the top, primary succession needs thousands of years to break down rock into soil. On the bottom, in secondary succession, seeds germinate quickly, skipping the millennia of chemical weathering required the first time. The result is an aggressive resurgence of life. Roots expand to stabilize the ground, utilizing the nutrient-rich ash to rebuild the canopy in mere decades. Ecological succession functions as a predictable, deeply embedded system of planetary resilience. It dictates exactly how life responds to sudden ruin. Devastating events in nature act as evolutionary mechanisms for renewal. Whether breaking down volcanic rock or rising from the ash of a wildfire, life is designed to perpetually rebuild.